I already discussed first topic of graph theory, that is graph terminology. There I discussed what is graph, what is edge, different types of graph like simple graph, multi-graph, pseudograph, directed graph, undirected graph, complete graph, bipartite graph, complete bipartite graph, and matching. Next topic is representing graph and graph isomorphism. One way is the graphical representation. In this topic, I will discuss how we can represent in list or matrix. So representation of graph, one way to represent a graph without multiple edges is to list all the edges. So you can just simply list all the edges, that is one way of graph representation. Another way using the adjacency list. We know if there is an edge between two vertices, then they are adjacent. So here we can write all the adjacent vertex. Let's see one example. Use adjacency list to describe a simple graph given in the figure. So this is a simple graph, no multi-edge, no self-loop. Now I will represent by using the adjacency list. Now for a vertex, B, C, E are adjacent. So that's why for A, adjacent will be B, C, E. For B, A is the adjacent. Now for C, A, E and D are adjacent. Next for D, E and C are adjacent. Then for E, A, D and C are adjacent. So we list out all the vertex and we will write all its adjacent. So that is a adjacency list representation. Next example 2, represent the directed graph by using adjacency list. In case of directed graph, we will consider the outgoing edge, not the incoming edge. So here is a directed graph. Now we will represent the adjacency list of it. So for A, its adjacent will be B, C, D and E. Now for A, B, C, D, E. Next for B there is a self loop. So B to B, then B to D. So B and D. Just mark E is not adjacent of B as there is a incoming edge. Okay, we'll just consider the outgoing edge. So there are no edge from B to E or B to A. That's why B adjacent will be B and D. Next for C, there is a self loop. So C will be adjacent to C. Then there are outgoing edge from C to E, C to A and C to C. So A, C, E. For D, there are no outgoing edge. There are incoming edge but no outgoing edge. So no adjacent. For E, D will be adjacent, B will be adjacent and C will be adjacent. So there is a edge to C, there is a edge to B, there is a edge to D. So B, C, D will be adjacent of E. So in case of directed graph, we'll just consider the outgoing edge, not the incoming edge in the adjacency list. So adjacency list is one way of representation. There is another way that called as adjacency matrix representation. For sparse graph, adjacency list representation is good. For dense graph, means there are multiple edges, there are more edges, adjacency matrix representation is good. In case of adjacency matrix, if there is a edge, then it will be 1. If there are no edge, then it will be 0. Suppose there are n vertices. In left side, we'll write all vertices and in top we'll write all vertices. If there is a edge, means if two vertices are adjacent, then it will be 1, else it will be 0. Suppose that G equals to VE is a simple graph where number of vertices equals to n and vertices are like V1, V2 till Vn. So in case of adjacency matrix, we will represent either 1 or 0. 1 means they are adjacent, 0 means they are not adjacent. So let's see one example. Use an adjacency matrix to represent the graph shown in the figure. This is the graph. Now I'll create the adjacency matrix. For this, there are 4 vertices A, B, C, D. So A, B, C, D. Here also we'll write A, B, C, D. A to A, no edges. So 0. A to B, there is a edge. A to C, there is a edge. A to D, there is a edge. So 1, 1, 1. If they are adjacent, it will be 1. If they are not adjacent, it will be 0. Now for B, A and C are adjacent. So for B, it will be 0. For D, it will be 0. Next for C, A and B are adjacent. For C, D, it will be 0. Next for D, A is the adjacent. For B, C, D, it will be 0. So this is the adjacency matrix representation. Just simple matrix representation is also okay. You can represent like this. You don't need to write all the vertices. But if you write the vertices, you can clear. Okay. Let's see another example. Example 4. Draw a graph with the adjacency matrix. Means one adjacency matrix is given. From that we'll draw a graph. So here let me consider A, B, C, D. 4 vertices. A, B, C, D. Now for A, B and C are adjacent. Then for B, A and D are adjacent. For B, A is already adjacent. Let this is D. D is adjacent. Next for C, A is adjacent, D is adjacent. C to A is already adjacent. So C to D is adjacent. Next for D, B and C are adjacent. Yes, B and C are adjacent. So this is the graph we draw from this adjacency matrix. So both graphs are same. You can check the adjacent. The adjacency matrix of a simple graph is symmetric. Means if A to B is 1, then B to A is also 1. Here you can see these two values are same. These two values are same. Means if there is a edge from B to A, then there is a edge from A to B. Because both of these entries are 1 when Bi and Bj are adjacent, else it is 0. So in case of simple graph, adjacency matrix representation is symmetric. When multiple edges are there, rather than 0, 1, we can write the number. Suppose between A and B there are 3 edges, we can write number 3. So that will be no longer 0, 1 matrix, that will be number matrix. We can use the large numbers because the ij entry in this matrix equals to number of edges associated with Bi and Bj. So all undirected graph including multigraph, pseudograph have symmetric adjacency matrix. So in case of multigraph or pseudograph also, their adjacency matrix is symmetric. Let's see one example. Example 5 is an adjacency matrix to represent pseudograph shown in the figure. Pseudograph means there are self loop, also there are multiple edges. Let's take A, B, C, D. Here A, B, C, D. Okay, so A, B, C, D. Now A to B there are 3 edges. Then A to D there are 2 edges. Next B to A there are 3 edges already done. B to C there is 1 edge. B to D there is 1 edge. Then C to B there is 1 edge already done. C to C there is 1 edge, so there will be a self loop. Then C to D there are 2 edge. Then D to A 2 edge. D to B 1 edge. D to C 2 edge. So this is the pseudograph. So in case of pseudograph, multi-edge and self-loop are allowed. Till now we discussed how we can represent adjacency matrix for undirected graph. For directed graph also we can represent by using the adjacency matrix. We will just consider the outgoing edge, out degree, not the in degree. So in case of directed graph, it will be 1 if there is a edge from Bi to Bj. And in case of directed graph, adjacency matrix is not symmetric. There may be a edge from A to B, but there are no edge from B to A. Just understand this. In case of undirected graph, adjacency matrix representation is symmetric, but in case of directed graph, adjacency matrix representation is not symmetric. Even in case of multigraph, pseudograph also it is symmetric if it is undirected, but in case of directed it is not symmetric. Let me take a small example. A to D there will be edge, A to B there will be edge, A to A and A to C are 0. Next B to C 1 and B to D 1, B to A 0, right? A to B there is a edge, but B to A 0. Next for C, C to D 1, rest all 0. Next for D, all are 0, all are incoming edge. So this is the adjacency matrix representation for this directed graph. We are considering just the out degree, not the in degree. Just the outgoing edges, not the incoming edges. If there are fewer edges, that call as sparse graph. And in case of sparse graph, adjacency list representation is good way. And in case of dense graph, adjacency matrix representation is a good way. So we can say the matrix for sparse graph as a sparse matrix, and the matrix for dense graph as a dense matrix. In today's lecture, I discussed how we can represent graph by using adjacency list and adjacency matrix. If this lecture is helpful for you, please like, share and subscribe. Thank you.